A DBMS supports the creation, usage, and maintenance of a database. It consists of several modules, each with their specific functionality that collaborate according to a predefined architecture. In this chapter, we zoom into this internal architecture and provide a categorization of DBMSs along various dimensions. It is based upon our book, Principles of Database Management, published by Cambridge University Press. You can find more information about our book on the website at the bottom of my slide. My name is Bart Basens, and I am one of the authors of the book. The overview of the chapter is straightforward. We start by discussing the components that together make up a DBMS. Next, we provide a classification of DBMSs in terms of data model, degree of simultaneous access, architecture, and usage. A DBMS needs to support various types of data management related activities, such as querying and storage. It also must provide interfaces to its environment. To achieve both these goals, a DBMS is composed of various interacting modules that together make up the DBMS architecture. This figure shows an overview of the key components of a DBMS architecture. We review each component in more detail in what follows. Note that the figure is by no means exhaustive. Depending upon the vendor and implementation, some components may be left out and others added. To the left, you can see various ways of interacting with the DBMS. DDL statements create data definitions that are stored in a catalog. Interactive queries are typically executed from a front-end tool, such as a command line interface, simple graphical user interface, or forms-based interface. Applications interact with the DBMS using embedded DML statements. Finally, the database administrator, or DBA, can use various database tools to maintain or fine-tune the DBMS. To facilitate all these usages, the DBMS provides various interfaces that invoke its components. The most important components are the connection manager, the security manager, the DDL compiler, various database utilities, the query processor, and the storage manager. The query processor consists of a DML compiler, query parser, query rewriter, query optimizer, and query executor. The storage manager includes a transaction manager, buffer manager, lock manager, and recovery manager. All these components interact in various ways depending upon which database task is executed. The database itself contains the raw data, or database state, and the catalog with the database model and other metadata, including the indexes that are part of the internal data model, providing quick access to the data. In what follows, we discuss each component listed here more extensively. The connection manager provides facilities to set up a database connection. It can be set up locally and through a network, which is more common. It verifies the logon credentials, such as username and password, and returns a connection handle. A database connection can either run as a single process or as a thread within a process. Remember, a thread represents an execution path within a process and represents the smallest unit of processor scheduling. Multiple threads can run within a process and share common resources such as memory. The security manager verifies whether a user has the right privileges to execute the database actions required. For example, some users can have read access, whilst others have write access to certain parts of data. The security manager retrieves these privileges from the catalog. The DDL compiler compiles the data definitions specified in DDL. Ideally, the DBMS should provide 3 DDLs, one for the internal data model, one for the logical data model, and one for the external data model. Most implementations, however, have a single DDL with 3 different sets of instructions. This is the case for most relational databases that use SQL as their DDL. The DDL compiler first parses the DDL definitions and checks their syntactical correctness. It then translates the data definitions to an internal format and generates errors if required. Upon successful compilation, it registers the data definitions in the catalog where they can be used by all the other components of the DBMS. The query processor is one of the most important parts of a DBMS. It assists in the execution of database queries such as retrieval of data, insertion of data, update of data, and removal of data from the database. Although most DBMS vendors have their own proprietary query processor, it usually includes a DML compiler, query parser, query rewriter, query optimizer, and query executor. The DML compiler compiles the data manipulation statements specified in DML. Before we explain its functioning, we need to elaborate on the different types of DML. Remember, DML stands for Data Manipulation Language. It provides a set of constructs to select, insert, update, and delete data. The first data manipulation languages developed were predominantly procedural DML. These DML statements explicitly specified how to navigate in the database to locate and modify the data. They usually started by positioning on one specific record or data instance and navigating to other records using memory pointers. Therefore, procedural DML is also called record-at-a-time DML. DBMSs with procedural DML had no query processor. In other words, the application developer had to explicitly define the query optimization and execution himself. To write efficient queries, the developer had to know all the details of the DBMS. This is not a preferred implementation, since it complicates the efficiency, transparency, and maintenance of the database applications. Unfortunately, many firms are still struggling with procedural DML applications due to the legacy DBMSs still being used nowadays. Declarative DML is a more efficient implementation. Here, the DML statements specify what data should be retrieved or what changes should be made rather than how this should be done. The DBMS then autonomously determines the physical execution in terms of access path and navigational strategy using a query processor. In other words, the DBMS hides the implementation details from the application developer, which facilitates the development of database applications. Declarative DML is usually set-at-a-time DML, whereby sets of records or data instances can be retrieved at once and provided to the application. Only the selection criteria are provided to the DBMS, and depending on the actual database state, 0, 1, or many records will qualify. A popular example of declarative DML is SQL. As an example, think about a Java application that needs to retrieve employee data from a database. It can do this by using SQL, which is one of the most popular querying languages used in the industry nowadays. In the Java program shown here, the SQL DML statements are highlighted in red. Without going into any language or syntax specifics, this Java application first initiates a database connection with a given username and password. Next, the application executes an SQL query which asks for the employee names together with their department names. It then iterates through the results, whereby at each step the employee name and corresponding department name is displayed to the screen. Many applications work with data stored in a database. To access a database and work with it, DML statements will be directly embedded in the host language. The host language is the general purpose programming language that contains the non-database related application logic. Obviously, both host language and DML should be able to successfully interact and exchange data. Embedding DML statements into a host language is not as straightforward as it may seem at first sight. The data structures of the DBMS and the DML may differ from the data structures of the host language. In our previous example, we used Java, which is an object-oriented host language, and combined it with MySQL, which is a relational DBMS using SQL DML. The mapping between object-oriented and relational concepts is often called the impedance mismatch problem. It can be solved in various ways. First, we can choose a host language and DBMS with comparable data structures. In other words, we combine Java with an object-oriented DBMS which allows transparent retrieval and storage of data. As an alternative, we could also opt to use middleware to map the data structures from the DBMS to the host language and vice versa. Both options have their pros and cons. This figure illustrates the impedance mismatch problem. To the left, we have a Java class employee with characteristics such as employee ID, name, gender, and DNR, which is the department number. It also has getter and setter methods to implement the OO principle of information hiding. To the right, we have the corresponding SQL DDL that essentially stores information in a tabular format, as you can see illustrated. The DML compiler starts by extracting the DML statements from the host language. It then closely collaborates with the query parser, query rewriter, query optimizer, and query executor for executing the DML statements. Errors are generated and reported if necessary. The query parser parses the query into an internal representation format that can then be further evaluated by the system. It checks the query for syntactical and semantical correctness. To do so, it uses the catalog to verify if the data concepts referred to are properly defined there and see if the integrity rules have been respected. Again, errors are generated and reported if necessary. The query rewriter optimizes the query independently of the current database state. It simplifies it using a set of predefined rules and heuristics that are DBMS specific. In a relational database management system, nested queries might be reformulated or flattened to join queries. The query optimizer is a very important component of the query processor. It optimizes the query based upon the current database state. It can make use of predefined indexes that are part of the internal data model and provide quick access to the data. The query optimizer comes up with various query execution plans and evaluates their cost in terms of resources required by aggregating the estimated number of input-output operations, the plan's estimated CPU processing cost, and the plan's estimated execution time into the total estimated response time. Obviously, a good execution plan should have a low response time. It is important to note that the response time is estimated and not exact. The estimates are made using catalog information combined with statistical inference procedures. Empirical distributions of the data are calculated and summarized by their means, standard deviations, etc. Coming up with accurate estimates is crucial in a good query optimizer. Finding an optimal execution path is essentially a classical search or optimization problem whereby techniques such as dynamic programming can be used. As already mentioned, the implementation of the query optimizer depends upon the type of DBMS and the vendor and is a key competitive asset. The result of the query optimization procedure is a final execution plan, which is then handed over to the query executor. The query executor takes care of the actual execution by calling on the storage manager to retrieve the data requested. The storage manager governs physical file access and as such supervises the correct and efficient storage of data. It consists of a transaction manager, buffer manager, lock manager, and recovery manager. Let's zoom into more detail. The transaction manager supervises the execution of database transactions. Remember, a database transaction is a sequence of read-write operations considered to be an atomic unit. The transaction manager creates a schedule with interleaved read-write operations to improve overall efficiency and execution performance. It also guarantees the atomicity, consistency, isolation, and durability or asset properties in a multi-user environment. The transaction manager will commit a transaction upon successful execution, so the effects can be made permanent, and roll back a transaction upon unsuccessful execution, so any inconsistent or bad data can be avoided. The buffer manager is responsible for managing the buffer memory of the DBMS. This is part of the internal memory, which the DBMS checks first when data needs to be retrieved. Obviously, retrieving data from the buffer is significantly faster than retrieving it from external disk-based storage. The buffer manager is responsible for intelligently caching the data in the buffer for speedy access. It needs to continuously monitor the buffer and decide which content should be removed and which should be added. In case data in the buffer has been updated, it must also synchronize the corresponding physical files on disk to make sure updates are made persistent and don't get lost. A simple buffering strategy is based upon data locality that states that data recently retrieved is likely to be retrieved again. Another strategy uses the 20/80 law, which implies that 80% of the transactions read or write only 20% of the data. Finally, when the buffer is full, the buffer manager needs to adopt a smart replacement strategy to decide which content should be removed. Furthermore, it must be able to serve multiple transactions simultaneously. Hence, it closely interacts with the log manager to provide concurrency control support. The log manager is an essential component for providing concurrency control, which ensures data integrity at all times. Before a transaction can read or write a database object, it must acquire a log which specifies what types of data operations the transaction can do. Two common types of logs are read and write logs. A read log allows a transaction to read a database object, whereas a write log allows a transaction to update it. To enforce transaction atomicity and consistency, a logged database object may prevent other transactions from using it, hence avoiding conflicts between transactions that involve the same data. The log manager is responsible for assigning, releasing, and recording logs in the catalog. It makes use of a logging protocol which describes the logging rules and a log table with the log information. The recovery manager supervises the correct execution of database transactions. It keeps track of all database operations in a log file. It will be called upon to undo actions of aborted transactions or during crash recovery. Besides the components we discussed before, a DBMS also comes with various utilities. A loading utility supports the loading of the database with information from a variety of sources such as another DBMS, text files, Excel files, etc. A reorganization utility automatically reorganizes the data for improved performance. Performance monitoring utilities report various key performance indicators, KPIs, such as storage space consumed, query response times, and transaction throughput rates to monitor the performance of a DBMS. User management utilities support the creation of user groups or accounts and the assignment of privileges to them. Finally, a backup and recovery utility is typically included. A DBMS needs to interact with various parties, such as a database designer, a database administrator, an application, or even an end user. To facilitate this communication, it provides various user interfaces such as a web-based interface, a standalone query language interface, a command line interface, a forms-based interface, a graphical user interface, a natural language interface, an application programming interface or API for short, an admin interface, and a network interface. Here you can see an example of the MySQL Workbench interface. You can see the navigator window with the management, instance, performance, and scheme section. The query window provides an editor to write SQL queries. In our case, we wrote a simple SQL query to ask for all information from the product table. The results window displays the results of the execution of the query. The log window provides a log with actions and possible errors. Given the proliferation of DBMSs available, we introduce a categorization according to various criteria in this section. We discuss categorization of DBMSs based upon data model, simultaneous access, architecture, and usage. Note that our categorization is not to be interpreted in an exhaustive nor exclusive way. It can thus be that a DBMS falls into multiple categories simultaneously. Also, other categories might be considered. Throughout the past decades, various types of data models have been introduced for building conceptual and logical data models. Hierarchical DBMSs were one of the first DBMS types developed and adopt a tree-like data model. The DML is procedural and record-oriented. No query processor is included. The definitions of the logical and internal data model are intertwined, which is not desired from a usability, efficiency, and maintenance perspective. Popular examples are IMS from IBM and the registry in Microsoft Windows. Network DBMSs use a network data model which is more flexible than a tree-like data model. One of the most popular types are codicil DBMSs, which implement the codicil data model. Again, the DML is procedural and record-oriented, and no query processor is available. Consequently, the definitions of the logical and internal data model are also intertwined. Popular examples are CA-IDMS from Computer Associates, UDS from Siemens Nixdorf, DMS 1100 from Unisys, and Image from HP. Both hierarchical and codicil DBMSs are legacy database software. Relational DBMSs, or RDBMSs, use the relational data model and are the most popular in industry. They typically use SQL for both DDL and DML operations. SQL is declarative and set-oriented. A query processor is provided to optimize and execute the database queries. Data independence is available thanks to a strict separation between the logical and internal data model. This makes it very attractive to develop powerful database applications. Popular examples are MySQL, which is open source and maintained by Oracle, the Oracle DBMS, also provided by Oracle, DB2 from IBM, and Microsoft SQL Server from Microsoft. Object-oriented DBMSs, or OODBMSs, are based upon the object-oriented data model. An object encapsulates both data, also called variables, and functionality, also called methods. When combining an OODBMS with an object-oriented programming language, such as Java or Python, there is no impedance mismatch, since the objects can be transparently stored and retrieved from the database. Examples of OODBMSs are DB4O, which is an open source OODBMS maintained by Versant, Cache from InterSystems, and Gemstone S from Gemtalk Systems. OODBMSs are not that popular in the industry beyond some niche markets due to their complexity. An object relational DBMS, or RDBMS, also commonly called an extended relational DBMS or ERDBMS, uses a relational model extended with object-oriented concepts such as user-defined types, user-defined functions, collections, inheritance, and behavior. Hence, an ORDBMS or ERDBMS shares characteristics with both an RDBMS and an OODBMS. As with pure relational DBMSs, the DML is SQL, which is declarative and set-oriented. A query processor is available for query optimization. Most relational DBMSs, such as Oracle, DB2, and Microsoft SQL Server, incorporate object relational extensions. XML DBMSs use the XML data model to store data. XML is a data representation standard. Native XML DBMSs such as base, X, and exist store XML data by using the logical intrinsic structure of the XML document. More specifically, they map the hierarchical or tree structure of an XML document to a physical storage structure. XML-enabled DBMSs such as Oracle, IBM DB2 are existing RDBMSs or ORDBMSs that are extended with facilities to store XML data and structured data in an integrated and transparent way. Both types of DBMSs also provide facilities to query XML data. Finally, the last few years brought us a realm of new database technologies targeted at storing big and unstructured data. These are often referred to using the umbrella term not only SQL, NoSQL databases, with popular examples such as Apache Hadoop or Neo4j. NoSQL databases can be classified according to data model into key value stores, tuple or document stores, column-oriented databases, and graph databases. However, even within such subcategory, the heterogeneity of the members is quite high. The common denominator of all NoSQL databases is that they attempt to make up for some shortcomings of relational DBMSs in terms of scalability and the ability to cope with irregular or highly volatile data structures. DBMSs can also be categorized based upon the degree of simultaneous access. In a single user system, only one user at a time is allowed to work with the DBMS. Obviously, this is not that desirable in a networked environment. Multi-user systems allow multiple users to simultaneously interact with the database in a distributed environment, as illustrated here, where 3 clients are being served by 3 server instances or threads. To do so successfully, the DBMS should support multi-threading and provide facilities for concurrency control. A dispatcher component then typically distributes the incoming database requests among server instances or threads. The architectural development of DBMSs is similar to that of computer systems in general. In a centralized DBMS architecture, the data is maintained on a centralized host, such as a mainframe system. All queries will then have to be processed by this single host. In a client-server DBMS architecture, active clients request services from passive servers. A fat client variant stores more processing functionality on the client, whereas a fat server variant puts more on the server. The N-tier DBMS architecture is a straightforward extension of the client-server architecture. A popular example is a client with the GUI functionality, an application server with the various applications, a database server with the DBMS and database, and a web server for web-based access. The communication between these various servers is then handled by middleware. In a cloud DBMS architecture, the DBMS and database are hosted by a third-party cloud provider. The data itself can then be distributed across multiple computers in a network. Although this is sometimes a cost-effective solution, depending on the context, it can perform less efficiently in terms of processing queries or other database transactions. Popular examples are the Apache Cassandra project and Google's Big Table. A federated DBMS is a DBMS which provides a uniform interface to multiple underlying data sources such as other DBMSs, file systems, document management systems, etc. By doing so, it hides the underlying storage details, in particular the distribution and possible heterogeneity of data formats and data management functionality to facilitate data access. An in-memory DBMS stores all data in internal memory instead of slower external storage such as disk. It is often used for real-time purposes, such as in telco or defense applications. Periodic snapshots to external storage can be taken to support data persistence. A popular example of an in-memory DBMS is SAP's HANA product. DBMSs can also be characterized based on usage. Online transaction processing, or OLTP DBMSs, focus on managing operational or transactional data. Think of a point of sale, POS, application in a supermarket, where data about each purchase transaction, such as the customer information, products purchased, the prices paid, the location of the purchase, and the timing of the purchase, needs to be stored. In these settings, the database server must be able to process lots of simple transactions per unit of time. Also, the transactions are initiated in real time, simultaneously, by many users and applications. Hence, the DBMS must have good support for processing a high volume of short, simple queries. Online analytical processing, OLAP, DBMSs focus on using operational data for tactical or strategical decision-making. Here, a limited number of users formulates complex queries to analyze huge amounts of data. The DBMS should support the efficient processing of these complex queries, which often come in smaller volumes. Big data and analytics are all around these days. IBM projects we generate 2.5 quintillion bytes of data every day. This is a lot compared to traditional database applications. Hence, new database technologies have been introduced to efficiently cope with big data. NoSQL is one of these newer technologies. NoSQL databases abandon the well-known and popular relational database scheme in favor of a more flexible or even schemeless database structure. This is especially handy to store unstructured information such as emails, text documents, Twitter tweets, Facebook posts, etc. One of their key advantages is that they also scale more easily in terms of storage capacity. We already mentioned 4 popular types of NoSQL database technologies, classified according to data model. Key value-based databases such as CouchDB, document-based databases such as MongoDB, column-based databases such as Cassandra, and graph-based databases such as Neo4j. Multimedia DBMSs allow for the storage of multimedia data such as text, images, audio, video, 3D games, CAD designs, etc. They should also provide content-based query facilities such as find images of Bart or find images of people who look like Bart. Streaming facilities should also be included to stream multimedia output. These are very resource-intensive transactions, which may require specific hardware support. Note that multimedia data is usually stored as a binary large object, blob, and supported by most modern-day commercial DBMSs. A spatial DBMS supports the storage and querying of spatial data. This could include both 2D objects such as points, lines, and polygons, and 3D objects. Spatial operations like calculating distances or relationships between objects such as whether one object is contained within another, intersects with another, is disjoint from another, etc. are provided. Spatial databases are a key building block of geographical information systems. Most commercial DBMS vendors offer facilities for spatial data management. A sensor DBMS manages sensor data, such as biometric data obtained from wearables or telematics data which continuously records driving behavior. Ideally, it has facilities to formulate application-specific queries, such as spatial temporal queries which ask for the shortest path between two locations given the current state of the traffic. Most modern-day DBMSs provide support for storing sensor data. Mobile DBMSs are the DBMSs running on smartphones, tablets, and other mobile devices. They should always be online, have a small footprint, and be able to deal with limited processing, power, storage, and battery life. Depending upon the context, they could connect and synchronize to a central DBMS. Ideally, they should be capable of handling queries and support self-management without the intervention of a DBA. Some popular examples are Oracle Lite, Sybase SQL Anywhere, Microsoft SQL Server Compact, SQLite, and IBM DB2 Every Place. Finally, open source DBMSs are DBMSs for which the code is publicly available and can be extended by anyone. This has the advantage of having a large development community working on the product. They are very popular for small business settings and in developing countries where budgets are limited. Most of the open source DBMSs can be obtained from www.sourceforge.net, which is a well-known website for open source software. Some examples are MySQL, which is a relational DBMS maintained by Oracle, PostgreSQL, which is also relational and maintained by the PostgreSQL Global Development Group, Twig, which is an object-oriented DBMS maintained by Google, and Burst, which is also an OODBMS maintained by MacObject. To conclude, in this chapter, we first zoomed into the architecture of a DBMS. We extensively discussed the components that together make up a DBMS. We illustrated how they collaborate for data storage, processing, and management. Next, we provided a categorization of DBMSs in terms of data model, degree of simultaneous access, architecture, and usage. Note, this categorization is by no means exhaustive nor exclusive, since the DBMS can support various functionalities simultaneously. For more information, we are happy to refer to our book, Principles of Database Management, published by Cambridge University Press. See also the website at the bottom of this slide.